Imagine logging into your university portal on registration day, clicking a few buttons, and accidentally enrolling in 10,000 classes that all happen at the exact same time. In the physical world, we know that's impossible. A person can only sit in one chair at one time. But computers completely lack human common sense. Without specific instructions, a system will gladly let a single student digitally occupy thousands of overlapping seats. To prevent this, database architects have to program the rules of reality into the computer. They have to teach the system how objects, like students, classes, and professors, are actually allowed to interact. Designers map these connections out using the entity relationship model, essentially a digital blueprint for how different things relate to one another. Within that blueprint, the foundational laws are called mapping constraints. Mapping constraints dictate exactly how many of one item can connect to another item. They are the ultimate defense against digital chaos, ensuring our data reflects the real world. Let's look at the first and strictest rule of database matchmaking, the one-to-one constraint. Think about the relationship between a person and a passport. A single person is issued at most one active passport, and that specific passport belongs to only one person. It is an exclusive pairing. This diagram shows how a one-to-one connection is formally sketched. Notice the arrows. Because the lines have a directed arrow pointing toward both entities, the database knows that neither side is allowed to share with anyone else. That double arrow structure guarantees a strict, mutual, singular ownership. If you pair a person and a passport under a one-to-one constraint, the database ensures neither side can ever be double-booked. Of course, not everything in life is strictly exclusive. That brings us to a much more common organizational structure, the one-to-many constraint. Picture a computer science department. That one single department employs dozens of different professors to teach all its classes. One department connects to many professors. But look at that exact same connection from the professor's point of view. From their perspective, the relationship works in reverse. Those many individual professors all belong to exactly one single department. We call this a many-to-one constraint. These panels show how both perspectives are drawn. The arrow always points toward the one side of the relationship. It caps the limit at 1, while the flat line allows for many. One-to-many and many-to-one are not different physical rules. They are the exact same database relationship viewed from different directions, depending entirely on which entity you start with. Now we reach the busiest, most crowded connection type, the many-to-many constraint. This is the situation we started with. One student enrolls in many courses. At the same time, one course holds many students. This diagram represents a many-to-many relationship. Notice the lack of directed arrows. Both sides use plain lines, leaving the connection completely open in both directions. However, relational databases cannot physically store a direct many-to-many relationship. If you try to wire them straight together, it creates a structural mess that the computer can't efficiently search. To solve this, designers build a bridge. They create a junction table, like a central enrollment roster. This bridge sits in the middle, splitting that messy web into two clean, manageable one-to-many relationships. Many-to-many relationships reflect the true, interconnected messiness of our lives. But to store that mess digitally, we rely on this structural compromise. Once we know the maximum number of connections allowed, we still have one missing piece. We need to know if the connection is mandatory. Architects handle this using a companion rule called a participation constraint. Think of a standard company payroll. Every single employee must be assigned to a department to get paid. Because the connection is mandatory for the employee, it's called total participation. On the other hand, the company might create a brand new department before they've actually hired anyone. The department can exist in the system with 0 employees. That makes its connection optional, which we call partial participation. Mapping constraints dictate the maximum limits of a relationship, while participation constraints dictate the minimum requirements for existence. When you combine these rules, you get a logical framework that keeps our information safe from chaos. Building a database is about deeply observing how people and institutions actually interact, then translating those human habits into logic. Mapping constraints are the digital mirrors of real-world logic. They sit quietly behind the scenes, maintaining order and making complex software possible.